Okay. So this is Unit 2, Lesson 5 for our Precalculus 12 class. Unit 2 is called Parent Functions, parent like your mom or dad. Lesson 5 is called Graphing Radical Functions. What we're going to learn in this lesson is how to understand the radical relationship. We're going to see what the graph of a radical function looks like, and we're going to learn how to graph a radical function by hand. So when we consider a radical function and connecting it to a geometric representation, we can use a radical function to relate the area of a square to the side length of the square, such that the square root of the area of the square is equal to its side length. So here's my square right here. If I set a equal to 4, then I'm saying I have a square with an area of 4. You could look at the graph and confirm this is indeed a square. There's 4 boxes inside, so its area is 4. The side length is 2. So when the area of the square is 4, the side length is the square root of 4, or 2. As we increase a, increase a to 9, we now have a square with an area of 9, and the square root of 9 is 3, so the side length of the square is 3. And we can make this square for any a value, any area. And if we do, we see not only does the area grow, but the side length grows. And then one observation, as the area grows, the side length is growing, but the more the area grows, the slower the side length grows. And this relationship between the area and the side length can be graphically represented by a radical function. So f of x equals the square root of x. If I plot that graph, we can kind of see it highlights the relationship of the area of the square with the side length of the square. We also notice that if we're talking about the area of a square, you can never have a negative area. So a can be 0 or greater than 0, but it can't be a negative value. It can't be less than 0. So that'll give us some domain restrictions, which will then give us some range restrictions. So we'll look at that at the graph. So if I want to graph the f of x, some function f of x, where f of x equals the absolute value, or sorry, the square root of x, I want to be smart about this. I want to try to avoid rational numbers and stick with just integers. I know the square root of 0, the square root of 1, the square root of 4, the square root of 9, those are all perfect square numbers. So if I plot those as my x values, I could easily get the y value. The square root of 0 is 0, the square root of 1 is 1, the square root of 4 is 2, and the square root of 9 is 3. So 0, 0, 0, 1, 1, 4, 2, 9, 3. The first 3 points I can map all 4 of these points on this graph, and we kind of get our radical function graphed. Like we said before, if we think of domain restrictions, like we said before, the area of a square can't be a negative number. So when we say domain, x has to be greater than or equal to 0, or we can write that in interval notation as from 0 to infinity, square brackets next to the 0, because we include 0 as a possible value in our domain, and normal brackets after the infinity, because infinity can't be contained. Now for our range, we can say, okay, what y values can I get out of this? So the range in this case, f of x refers to the side length of a square. And so if we think of a side length of a square can't be a negative number. So then my y values, or my f of x, has to be greater than or equal to 0. Another way of saying that is any value I put in for x, the only y values I can get for f of x is going to be 0 or a number greater than 0. So our range, we can say, is y is greater than or equal to 0, or we could say interval notation from 0 to infinity, square brackets on 0, because 0 is included. All right, some examples here. So if I wanted to graph f of x equals 2 times the square root of x plus 1, I could do that by hand, and this is kind of a Mr. Jansen's homebrew method of just making a table for a radical function. So since I'm working with square roots, the square roots that I can do without having to worry about decimals or fractions, or as little as possible worry about fractions, is sticking with the perfect squares. So my first point, I want to get the radical to be square root of 0. I want to get square root of 1. I want to get square root of 4, and so on. 9, 16, 25, perfect squares. Probably not going to get to 9, let alone 16 or 25, but we'll try them out just for practice. So if I want to get the square root of x plus 1 to equal the square root of 0, then x has to be negative 1. And that makes sense because negative 1 plus 1 equals 0. So if I put x as negative 1, that makes the radicand, or the thing underneath the radical sign, equal to 0. If I make x equal to 0, I can get a radicand of 1. If I make x equal 3, I can get a radicand of 4. X equals 8 gives me a radicand of 9, and x equals 15 gives me a radicand of 16, because we're adding 1 every time, right? And so what I want to do is I want to take those numbers, negative 1, 0, 3, 8, and 15, and those are my x values that I'm going to plug into f of x and evaluate. So I'm going to plug them back in to the original function this time, not just the square root of x plus 1, but the whole thing. So 2 times the square root of x plus 1. If I plug in negative 1, I get 2 times the square root of 0, which is just 2 times 0, 0. The second one, if I plug in 0 for x, I get 2 times the square root of 1, which is just 2. The next one is 2 times the square root of 4, which is going to be 2 times 2, which is 4. 2 times the square root of 9, which is going to be 2 times 3, so 6. And 2 times the square root of 4 is going to be, 2 times the square root of 16, that's going to be 2 times 4, which is going to be 8. And we're at the point where we're kind of off the graph of our window we've got going on here, so I'm probably not going to graph 15, 8, but the rest of these points I can graph. Negative 1 maps to 0, 0 maps to 2, 3 maps to 4, and 8 maps to 6. And here's that graph right there. We notice that our domain has shifted a little bit. So our initial value to make a square with an area of 0, you could think, is when x is equal to negative 1. So x has to be greater than or equal to negative 1. Our interval notation would be negative 1 to infinity with the square bracket on negative 1. Our range has not changed. Our lowest y value is still at the x-intercept, or the x-axis. And so y could be 0, or y could be anything greater than 0. So we say y is greater than or equal to 0, or we could say in interval notation 0 to infinity, including 0. All right, takeaways. So we've looked at the graph of a radical function. And I guess we could talk about radical function as being half of a parabola. So if I take a parabola and I tilt it on its side and I cut off the negative half, that's basically what this is right here. And that kind of could make sense intuitively because a square root function is the inverse of a square function.